In this video, we're going to look at moments and center of mass, not momentum, moments, typo, moments and center of mass. Just go ahead and give you a little forewarning. This is going to be a wordy section. It's got a lot of definitions we got to get through. It's going to take a little bit of time, and I'm going to write things as I go, just so I can really explain things as we go. Okay, so it's going to take a little time to really get into this, so bear with me. So the first thing that I want to do is I want to think about some masses. Let's place a fulcrum. And let's place that at the origin just to give us a bearing. So this will be the point 0, 0. And then what I'm going to do is I'm going to place some masses along this axis. So we'll have mass 1 at position x1. We'll have mass 2, position x2. We'll have mass 3 at position x3. So I think we all know how masses work, right? If this side weighs more, it's obviously going to turn around the fulcrum. If the left-hand side weighs more, it's going to be rotating counterclockwise. And then if everything were balanced, then it's going to stay level. So each mass exerts a downward force. And that's what gives it its twisting nature. And that force, we can think of any force as the mass times gravity. And that g is the acceleration due to gravity. So approximately 9.8 meters per second squared. So force we can think of as mass times gravity. Use my capital F there, where gravity 9.8 meters per second squared. So M1, M2, and M3 could all balance if the weights and distances balance. So remember what we were saying before is if we have this mass way out here, that's going to be applying a greater force on the system because of its position. So if all these weights and distances align, so this mass would have to be smaller than this mass, and there's a second mass over there as well on the right hand side. So together those two masses have to weigh less than the third one if that third mass is really that far out compared to the first mass. So if all those things balance out, then it won't move. However, if the forces do not balance, if the distances and weights don't balance, the beam will become uneven. It will not just stay completely horizontal as it is now. This turning effect is torque. T-O-R-Q-U-E. So just to formally define this new word, torque. A twisting force that leads that tends to cause rotation. That tends to cause rotation. So you probably have heard of a torque gun or a torque wrench. Think of what mechanics use to take off lug nuts, because what that wrench is doing, or what that mechanical gun is doing, is it's turning a lug nut, it's turning that nut, and that is a turning force. That is why it is a torque. It's applying torque to the system being just a simple lug nut. The three masses in the picture above. Each exert their own torque. M2 and M3, because they're pushing downwards, they are exerting a clockwise torque. M1 is pushing downwards, it is exerting a counterclockwise torque. If we think of these clockwise torques, those are negative torques, because if we think about moving through an angle downwards like that, that is a negative angle, versus if we're moving in that counterclockwise direction, that is a positive torque. So M2 and M3 are exerting the clockwise negative torque. M1 is exerting the counterclockwise positive torque. So I put clockwise and counterclockwise in parentheses because we would refer to these as negative and positive. I'm just giving you the clockwise and counterclockwise for the visualization since we are new to this torque, but we would typically call these a negative and a positive torque. The sum of the torques is called the system torque. And measures the tendency of the system to rotate about the fulcrum. All right, so we've defined torque, we've seen system torque, we understand how things move in a positive, negative direction. Let's just write down the equation for this system torque then. The system torque is equal to mass 1 times gravity, which is the force, x1, plus mass 2 times gravity, which is the force, times x2, plus mass 3 times gravity times x3, which notice we can factor out the gravity, and we would be left with m1 x1 plus m2 x2 plus m3 x3. Gravity here is called a feature of the environment. That part of the equation, the g, it's given to us by whatever system we're in. If we're on Earth, it's at 9.8. If we're on the moon, it'd be a different number. So wherever the environment of the system is, that is that g. The part that we can influence is the part in the parentheses, the part I've just underlined in green. That is the feature of the system. So system. We create the part in green. That's what we control. The part in blue, or the area in blue, we have no control over that aspect of it. The system will balance if and only if, IFF stands for if and only if, its torque is 0. And that makes sense, right? If everything balances out, this equation just gives us a big old 0, meaning nothing is actually moving. The number we get by doing the calculation m1 x1 plus m2 x2 plus m3 x3, the feature of the system, is called the moment of the system about the origin. Because remember, we set the fulcrum at the origin. It's the moment of the system about the origin. The feature of the system, that number we get when we calculate that moment of the system about the origin. It is the sum of the moments m1, x1, m2, x2, m3, x3 of the individual masses. So this makes sense, right? We can look at the system as a whole, or we can look at each component. If we look at each component or each mass exerts a force. M1 times G, M2 times G, M3 times G. We knew that before. If we put a couple of kids on a playground and we put them on a seesaw, each kid is exerting their own force. Now that might be in balance if they were to weigh the same, they're not kicking. However, it might be out of balance if one kid weighed more, if it was sitting further towards the end. We've understood that for a while. We're just bringing in some definitions. We're saying that if that seesaw is moving, then we are applying torque. The system is non-balanced. We're now defining moments as the mass times how far away they are. We're now looking at not only do we have two equidistant things, two kids sitting an equidistant amount from the fulcrum, what if they're sitting at different positions along that seesaw as well? And so each little mass has its own moment. The moments of the system, the moment of the system, moment of the system about the origin. The moment of the system, remember, is everything together. So that is equal to the sum, okay, is equal to 1 to however many we have. We've been working with 3 masses, but we could have any number of masses, mk times xk. That is just generalizing this a little bit for us. Now, if we do have that system out of balance, so coming back up to here to our original picture, if these two forces on the right are applying more force, obviously that side is going to go down. But what could we do then to put the system into balance? We could move the masses if we wanted to. We could move their distances from the fulcrum. We could change the masses. But what if we can't change that? What if we want to change one simple element? What if we could change the fulcrum? Well, then we could drive that system back into balance. We can shift the fulcrum to make the system balance. So think about that initial picture we had. We initially had our fulcrum right here, M1, M2, M3 at their respective positions. If we found that right-hand side was out of balance, what if we shifted that fulcrum? So where we used to have an old position x1, position x2, position x3, compared to the origin, we can think about how far they have now moved. So the torque of mk about, well, let's define this new fulcrum point. We need a number for it. Let's define it as x bar. So x bar is going to be that new fulcrum point. Well, then we can calculate these new torques. So the torque of mk about x bar is equal to the displacement of mk from x bar times downward force. Which we can write a little bit more efficiently as xk minus x bar. How far have we moved it? times mkg. Thus, to find where to place the fulcrum, the summation xk minus x bar is equal to 1 to n, however many we have, times mkg. We want that to be equal to 0. We can solve this equation, and we get x bar is equal to the summation mk xk over summation mk. K is equal to 1 to n, k is equal to 1 to n. So remember these mk, xk's, those are called the moments, or we have the moment of the system over the masses of the system. And what this gives us, x bar is called the system's center of mass. Center of mass. If we want to figure out how to put that system in balance, where do we need to move that central point to so it all balances? We need to calculate the center of mass, which we can do by taking the moment of the system and dividing it by the system's mass. Now, we can also calculate density. Delta x is equal to the limit, as x goes to 0, of the change in the mass over the change in position, which we can think of as dm dx. So what this allows us to do is to calculate the mass, right? If we want to calculate mass, we need its density. Mass is equal to the integral from a to b of the density of the object, dx, and then the moment about the origin, which we can define as m0, is equal to the integral from a to b of x delta x dx. Because remember we said the moment before was simply equal to the x times the force. Well, we're saying that the mass is this density curve. And then finally, we have an equation for center of mass. X bar is equal to moment over the mass. So we have an equation for mass based on a function's density. If we had that mass given to us directly, we could just use it. But if we have it in terms of density, and then the moment would be equal to the position times that mass dx. And that will give us the three equations that we're going to use for these first few problems. Now, this is one section that on the test I will give you some formulas, because there are going to be a lot of formulas. We're not even done yet. There's going to be a lot of formulas on this section. These three are three of the easier ones. However, for this section, this video that we're going to be doing, you do not need to just memorize formulas. You need to know how to use those formulas, but I will give you formulas on the test. So let's go ahead and take an example. What we want to do, we are going to find the mass. We're going to find the center of mass of a linear wire given the interval and given its density. So find the mass m and the center of mass the x bar, not the m bar, but the x bar, given a linear wire with density delta x is equal to 1 over x plus 1 on the interval 0 to 3. So the density of the wire is changing, but it does stay two-dimensional because we are only looking at that that wire's density changing. We don't have some sort of sheet or a surface, a three-dimensional surface. So we are thinking about just that linear wire here with changing density. If we want to calculate the mass, we know that we're going to take the integral from 0 to 3 of the density over x plus 1 times the dx. And so when we do this, we're going to take our antiderivative. That would be the natural log of x plus 1, and it would be the absolute value. Granted, we're only plugging in positive values, so that would be pretty straightforward. So we'll have the natural log of 4 minus the natural log of 1, natural log of 1 just being 0, so we get the natural log of 4. There is our mass. I'm just going to leave it in terms of natural logs. We can approximate if we want to by just typing this into the calculator, but I'm just going to find these in terms of exact values. So there is our mass. Next, we want to find the center of mass. Well, for the center of mass, remember our equations. Found our mass. Center of mass, x bar is equal to the moment about the origin over the mass. So we need to find our moment about the origin first. We weren't explicitly asked for that, but we're going to have to find it. So m naught is equal to the integral a to b of x times 1 over x plus 1 dx. All right, so the A and B I meant to make the 0 and the 3. There we go. All right, so I look at this. This is not as easy of an integral to calculate because I don't know how to do this antiderivative. But I can think of this using, I need to do my division. I need to look at what it would be as two different polynomials. X plus 1 can go into x with a remainder. So let's divide this out. X plus 1 goes into x one time, and so when we multiply that, we'd have x plus 1, subtract, and we get a negative 1. And so that is our remainder, and so we can write that as a negative 1 over x plus 1. So what we can do is we can write this as the integral from 0 to 3 of 1 minus 1 over x plus 1 dx. So anytime that numerator variable has the same power as the denominator, we can divide those, and we're just going to use our long division to divide those out. So now we can do the antiderivatives. We'll have x minus the natural log of the absolute value of x plus 1. We're going to evaluate this whole thing from 0 to 3. So plug in our 3 minus the natural log of 4, still positive, so I don't need the absolute values at this point, minus 0 minus the natural log of 1, natural log of 1 still being 0. And so we get 3 minus the natural log of the absolute value of 4, just 3 minus the natural log of 4. There is our moment. And so then finally we need to calculate our center of mass. Center of mass x bar is equal to the moment, 3 minus the natural log of 4, over the natural log of 4, which was our mass itself. And so there's our answer. So once we understand, or once we have those equations, relatively simple calculations, simple integrals, we just have to know those equations. And like I said, I don't expect you to memorize all the formulas in this section. For the most part, I do want you to know formulas in this section. There will be a lot of them. So that was for a simple one-dimensional wire, right? Just a wire running along a path. But what if we work in a plane? Not just looking at that seesaw anymore, but we have some sort of totter platform where we have a whole entire plane that we are looking at. So we have our x-axis, we have our y-axis, and we have our origin. 0, 0, the origin. So we might have a y position, and we might have an x position. And that's where our mass now lies. Each mass has a moment about each axis. This mass, just like before, when we ignore the y-axis, we just look at this x-axis here, we can see it has depth to it. And so that has a force that's trying to twist it around. The y-axis, same exact thing. The y-axis has a depth to it now, so it's trying to twist around as well. So each axis has its own moment, or each mass has its own moment about each axis. The moment about the x-axis, mx, is equal to the sum of the masses times the y's. Now you might be saying, well, why the y's? Think the x is twisting about that y. And so if we're twisting about the y, if we're thinking about the moment about the x, how we're twisting around the x-axis. So how are we looping this axis right here? Didn't switch colors. But if we're thinking about looping that axis right there, we're thinking about how far away from the x-axis are we, how far up or down, what are the y values there? And then the moment, there it goes, always on its delay, the moment about the y-axis. Let's see if I can clean this up real quick. There we go. So moment about the y-axis, my is equal to the summation of mk xk, for the exact same reason we talked about. If we were thinking about rotating about the y-axis, well, now we're thinking about how far left and right are we that would be causing that sort of rotation. All right, so let's think about the center of mass then. The systems, try that again, systems center of mass x bar, y bar, found x bar is equal to the moment about the y over the mass, which is equal to the summation of the mk, and remember the my was the x, okay, over m, over the summation of the mk. And y bar is going to be equal to the mx over m, which is equal to the summation of masses times y positions over summation of the masses. So again, we have yet another formula here, but it's kind of making sense, or hopefully at least it makes a little bit of sense. All right, so if we think about a thin, flat plate, and whatever it looks like, right, just has some sort of odd shape to whatever it is. Let's take a strip of that plate. So I'm cutting out just a strip. Strip of plate. The strip has mass delta m and center of mass, call it x, y, wiggle. X wiggle, y wiggle. And so somewhere on this strip there is going to be a center of mass, depending on how it's aligned. Try and get that a little bit more towards the center. That strip will have its own center of mass based on how much mass is in that, the delta M. We can get the moments here about the x-axis. Mx is equal to the integral of y dm. And the moment about the y-axis is equal to the integral x wiggle dm. Calculating each of these moments of the strips independently, and then we'll be able to join up all these strips. So then the mass is equal to integral dm, and the center of mass x bar, y bar equal to the moment of the y over m and the moment of the x over m. And now we can put this together in an example. Let's find the center of mass of a thin plate of constant density delta covering the region bounded by the parabola y equals 25 minus x squared and the x-axis. Okay, so the first thing I'm going to do is start with a sketch. Y equals 25 minus x squared. This is the region that we are looking at, the shaded region here. Now, one thing that's occurring to me right away is it is balanced around the y-axis. So already I know that that center of mass for the x is going to be 0 because it is balanced equally over here and over here. If we were looking at a circle, it'd be the same story on both the axes. But clearly the y is not just at 0. There's the y where it's balanced, it goes up some here. Not changing colors again, but that's all right. So the y, we need to figure out where that center needs to lie so that we can balance this parabola on that point. So I think essentially we're cutting out a shape, and what we want to do is figure out where can I put my pencil underneath that shape so that it stays perfectly balanced. Where on this weird looking seesaw do I need to put the fulcrum so that it will just completely balance? So obviously it's in the dead center on the x-axis. What about on that y-axis? So let's start thinking about the center of mass of a strip. So x wiggle, y wiggle. The point x wiggle, y wiggle. That'd be equal to x comma 25 minus x squared over 2. We want everything in terms of one variable x so that we can work with it. We have any position x. For any position x along that, the height would be 25 minus x squared over 2 because we want for that little strip, I'm not switching colors again, but that's fine. Obviously, where the y's are going to balance is exactly in the middle. So if we have that tiny little strip, the y's will balance in the dead center. So 25 minus x squared, the y over 2. the length of that strip is equal to 25 minus x squared. Simply the y function, because we're measuring from the x-axis up. So the length of this thing, L, is equal to 25 minus x squared. And then the width, that is given to us by the dx, however far we have moved. And so then if we think about the area, or the change in area of that little strip, the dA, the area of that little strip, that is equal to 25 minus x squared times dx, length times width. The area is equal to length times width. And so if we're thinking about that little change in area, this little piece right here, that little strip, dA is equal to 25 minus x squared dx. So now we can begin to calculate the moment of about the x-axis. Moment about the x-axis, remember mx is equal to the integral of y squiggle dm. And so if we think about the y squiggle, we know what that is. That is 25 minus x squared over 2. dm must be equal to 25 minus x squared dx times the density. Let me squeeze that in there. So let's see if I can get this change colors. There we go. This portion right here is the dm. Why is that? Well, dm must be equal to the change in area times the density. We're told that the density is set, that delta in there it's a fixed number, it's constant, so we're multiplying that by the area. So now what we can do is we can pull that delta to the front. Oh, the other thing I need my integration limits. So we need to think about where we're going to and where we're going from. So where does this thing touch the x-axis? We haven't done that yet. We need the limits. So when is 25 minus x squared equal to 0? Can be over x squared over, take the square root, x is equal to plus or minus 5. So those will be our limits. We needed that piece of it as well. So the limits going from negative 5 to 5 of 25 minus x squared over 2 times 25 minus x squared dx. I can go ahead and pull out that 1/2 too. That would have been an easier step just a second ago. So delta over 2 from negative 5 to 5. Now we need to multiply this together. So 25 times 25 should give us 625. 625. Let me just rewrite that. It's really ugly. 625. 25 times negative x is negative 25x, and then we have to double it, negative 50x, and it's really squared. Then we have x squared times x squared, which gives us x to the 4th. So we'll have delta over 2, negative 5 to 5. And really we can just go ahead and integrate this at this point. So we're going to have 625x minus 50 over 3 x cubed plus x to the 5th over 5. And we're integrating from negative 5 to 5. And notice this was an even function, so really what I could do to make this a little bit easier is I could just integrate this from 0 to 5 and double it. So let me do that just to make it a little easier on myself.
Actually, let me go back and correct this. That should be over 5 if I copy correctly from my previous line. So now let's just go ahead and start simplifying. So we have the 2 times 1/2, so that just gives us a delta out front. 625 times 5, we get 3,125. We're going to subtract. We have 5 cubed times the 50. That'll be 6250 over 3. And then we have 5 to the 5th over 5, which we could just write as 5 to the 4th, which is 625. In order to add all of these things, I need a common denominator, and that will be 3. So we'll have should give us 5,000 over 3. Just making sure I did all that right. That looks good. And so that gives us our moment about x, 5,000 delta over 3. And remember, that was the moment about x, how it moves with respect to the y-axis. So now that I have that, I still need to find the mass of the system. The mass of the system is what we have to divide by. So remember, mass of the system, we are going to take the integral of dm, which is equal to the integral. Well, our region is from -5 to 5, same region. And then our dm is the delta times the height times our width, which is the dx. So we'll get delta, it's constant multiple. Antiderivative 25 is 25x. X squared, we get x cubed over 3. We need to evaluate that from -5 to 5. That is another even function, so if we wanted to, I could have just written it as 2 delta and gone from 0 to 5. Let me actually just go ahead and change that up here. I think I'll make it a touch easier. So change that to 0, change that to 2 times 2 there, and I change this to 0. And so we'll plug in the 5, we'll have 25 times 5 minus 5 cubed over 3. And then we'll subtract off what we get when we plug in 0. And of course, if we plug in 0, we're just getting 0. So we will have 2 delta. 25 times 5 is 125 minus 125 over 3. So just like before, we need to get our common denominator, which will be 3. We'll have the 125 times 3. 325, subtract the 125. That gives us 250. So we'll get 2 delta times 250 over 3, giving us a total mass of 500 over 3 delta. So there is the mass of the plate, or the mass of our geometric figure. We are trying to find the y bar. We already knew that the x bar was equal to 0. So remember, the y bar, we simply take the moment about x and divide it by the mass of the system. So we'll have mx divided by m. Mx from before, well, let me just go and write down the m. We'll have 500 over 3 delta. And our mx, let me skim back up real quick. That was 5,000 over 3 delta. So we can cancel out the 3 in deltas easy enough, and 500 goes into 5,000 10 times. So our center of mass will be equal to the point x bar, y bar. X bar was 0, y bar we've just found to be 10. And there would be our center of mass. Let me skim back up to my picture real quick. Here, there it is. If we look at this picture, just think about it for a second. We know that this point right here is 25 because this was a parabola shifted up by 25 units and then reflected. And as we talked about, it makes sense that the center is going to be on the y-axis. That's why our x bar is 0. It also makes sense, just looking at the picture, we see there's a lot more mass on the bottom half of this figure. So the halfway point, 12.5, we would expect that center mass to be slightly under that because, again, the mass is hanging out in the bottom of the system. And so we have what appears to be a valid number. Logically, it makes sense. It's within our range. I'm going to define one last term. Get to an open space here. And my tablet's decided to stop working here all of a sudden. There we go. And that last term is a centroid. A centroid is the center of mass for a plane or a solid or whatever we have, a region with consistent density. Make that a little bit bigger if I can. My tablet's just decided it doesn't want to do anything. Let me see if I can zoom in on that so you can see a little bit better. There we go. Alright, so a centroid is a center of mass for this geometric plane with a constant density. That's exactly what we just did in the last problem. Remember, we had that density that canceled out. Trying to skim back up to it. I'm never going to find it again now because my tablet, like I said, being a pain. But when we found that x bar and that y bar, yeah, like I said, I'm not going to find it. There we go. When we found that measurement about x and that measurement about y, they had densities in them. When we found the mass, it also had a density in it. So what ended up happening is those densities canceled. That is because the density throughout the object was constant. That density remained the same the entire time. And so that centroid is that region with a consistent density. Now, what does that mean? Well, it means the problem's a little bit easier because we don't have to really worry about it. It's not changing. We don't have to come up with some density equation and work that into our integral. It also makes it a little bit easier because the densities just cancel off. But what that also means is that the center mass is a feature of the geometry, not of the material from which it is made. Feature. What this means is, we have something consistent. So for instance, maybe we're cutting out a shape from a piece of paper. That paper has consistent density. It doesn't matter what the paper is made of. To find the center of mass, we can ignore the material. It's just looking at the geometric figure in front of us. It doesn't matter if we have that piece of paper or if we instead we're cutting out a piece of tinfoil. No matter the material, the center of mass is a feature of the geometry, not of the material. Now, there are times that the material does matter. You could have a material where it's an inconsistent density. Don't just think about having different depths, right? You could have something with different depths that near ring in a third dimension, kind of like a rock. It has different shapes, on the x-y axis and also on the z-axis, but it could also have different densities. So it could be a completely flat plane that maybe part of it's made out of tin, which is relatively light material, and then part of it's made out of lead, which is a much, much heavier material. And so in these cases, we would have to incorporate that density. That density would have to be part of our equation when we're setting up that mx over m, my over m. The densities aren't going to cancel. We'd have to figure out what the densities would do inside of our integrals. In the case of a centroid, the densities will cancel by the end of the equation. So it's not relevant what the density actually is for finding center of mass. It just matters the geometric shape.